Welcome back to TalkTensors, listeners. Today, we're diving deep into a paper that caught our eye in the world of medical imaging.
Yeah.
It's focusing on something called intracranial hemorrhage, or ICH for short.
ICH, yeah.
And it uses CT scans to do rapid and accurate classification, which is, in the medical field, quite important, as you can imagine.
For sure.
So ICH is a type of stroke.
Right.
But it's not the most common one.
Right. It's only about 10 to 15% of all strokes.
Okay.
But it's way more deadly.
Oh, that's scary.
Yeah. So it has a much higher mortality rate and a much higher disability rate. So it's really important to be able to quickly and accurately diagnose this condition.
So what is this paper proposing? How are they using AI to help with that?
Okay. So the key thing here is that there are different subtypes of ICH. You can have bleeding in different locations within the brain.
Right.
And so they're using a specific type of AI model called a pyramid vision transformer.
A pyramid vision transformer.
Or often called a PVT. And they're using this to classify these different subtypes of ICH based on CT scans.
Right. And why is that important? I mean, why do we care about classifying the subtypes?
Well, the treatment can vary a lot depending on where the bleeding is occurring. So, if you have a bleed, say, within the brain tissue itself, that's called intraparenchymal hemorrhage.
Okay.
But if it's in the fluid-filled spaces, the ventricles, that's interventricular hemorrhage. And then you have things like epidural hemorrhage, subarachnoid hemorrhage, subdural hemorrhage. All these have different implications in terms of how they need to be managed.
So by quickly and accurately identifying which subtype it is, you can get the patient the right treatment much faster.
That's exactly right. And that can be life-saving, literally.
That makes a lot of sense. Now, is this something that radiologists are already doing? I mean, are they already good at classifying these subtypes?
They are. I mean, radiologists are highly trained professionals.
Right.
But even for experienced radiologists, it can be a really challenging task.
Yeah.
These CT scans, they can be very complex,
right.
And there can be subtle differences between the subtypes. And, in an emergency setting, when time is of the essence, that can be a real pressure cooker situation.
So having an AI system that can assist with this diagnosis could be a huge benefit.
Absolutely. It could potentially improve accuracy, it could reduce variability between different radiologists, and it could also just help to speed up the whole process.
So it's not necessarily replacing the radiologist, but it's more like a powerful tool to assist them.
Precisely. It's like having a second pair of eyes, maybe even a more specialized pair of eyes, looking at those images.
And those eyes never get tired.
Exactly.
Okay, so we know the problem they're trying to solve. Let's get a bit more into the technical details. You mentioned this pyramid vision transformer, the PVT. Can you explain a bit more about how that works and why they chose that particular model?
Sure. So PVTs belong to a family of deep learning models that have really revolutionized computer vision in recent years.
Right.
And they're called transformers. Now, traditional deep learning models for image analysis, they've largely relied on something called convolutional neural networks.
CNNs. We've talked about those before.
Yes, CNNs. And they've been incredibly successful. But they have certain limitations, especially when it comes to understanding global context and long-range dependencies within an image.
What do you mean by global context?
So imagine you're looking at a picture of a cat sitting on a mat. A CNN might be very good at recognizing the cat's features, the ears, the eyes, the whiskers.
Right.
But it might not be as good at understanding the relationship between the cat and the mat. It might not immediately grasp that the cat is on the mat, that those two things are related spatially.
Okay.
And that's where transformers come in. Transformers are really good at capturing these kinds of relationships, these global dependencies. They use something called an attention mechanism.
Attention.
Yeah. And attention is basically a way for the model to focus on the most important parts of the input.
So it's like the AI is paying attention to specific details that are relevant.
Exactly. And the really cool thing about transformers is that they can do this attention across the entire image, not just locally. So they can really understand how different parts of the image relate to each other.
So in the case of a CT scan, it can see how different slices relate to each other, not just what's happening on one slice in isolation.
Exactly. And that's why they're so well suited for this kind of medical image analysis where you have these complex 3D structures and you need to understand how everything fits together.
Right. Now you said PVT, pyramid vision transformer. What's the pyramid part about?
So the pyramid part refers to the hierarchical structure of the model.
Okay.
It basically processes the image at multiple scales, from very fine details to more coarse global representations.
So it's like looking at the image through a pyramid with different levels of detail.
Exactly. And this is important because different types of information might be relevant at different scales.
Right. So for example, a tiny bleed might be a crucial detail on a small scale, but its position relative to other brain structures might be more important on a larger scale.
Precisely. And the PVT is designed to capture both of those levels of information.
That's fascinating. So they feed these CT scans into this PVT model, and it starts extracting all these features, these different levels of information. But then they do something really interesting, right? They don't just use all of those features.
Right. That's one of the things I really liked about this paper. They use a very intelligent feature selection method based on something called SHAP values.
SHAP values.
Yeah, SHAP stands for Shapley Additive Explanations.
Etching name.
It is. And it's basically a way of understanding how much each feature contributes to the model's prediction.
So it's like assigning an importance score to each feature.
Exactly. And then they can rank the features by their importance and only select the most important ones.
And why is that important? Why not just use all of them?
Well, for a couple of reasons. First, using fewer features makes the model much more computationally efficient.
Makes sense. Less data to crunch.
Right. And that's important in a medical setting where you want the diagnosis to be as fast as possible.
For sure. Every second counts.
Exactly. But the other reason is interpretability.
Oh, right. We talked about that before.
By only using the most important features, it becomes much easier to understand what the model is basing its decisions on.
So the doctor can look at it and say, okay, the AI is focusing on these specific areas of the brain, these specific patterns.
Exactly. And that helps to build trust in the model.
Makes sense. Now, before they apply the SHAP analysis, they first reduce the dimensionality of the features using something called principal component analysis, or PCA.
Right. So PCA is a statistical technique that essentially finds the most important directions of variation in the data.
Okay.
And it allows you to represent the data using fewer dimensions while still preserving most of the important information.
So it's like compressing the data without losing too much detail.
Exactly. And in this case, they reduce the number of features down to the top 50 principal components.
And then they apply SHAP to those components to figure out which ones are the real heavy hitters, the ones that matter most for the classification.
Exactly. And they set a threshold, I think it was 1%. So any feature that contributed less than 1% to the model's decision was discarded.
Okay. So now we have this streamlined set of really informative features. What do they do with them?
So then they feed these features into what's called a boosting neural network.
Boosting.
Yeah, boosting is a really powerful machine learning technique where you combine multiple weak learners.
Weak learners.
Right. So a weak learner is just a model that's slightly better than random guessing.
Okay.
And the idea is that you combine a bunch of these weak learners together, and each one focuses on the mistakes that the previous ones made.
So it's like a team effort. Each model learns from the other's weaknesses.
Exactly. And by combining them together, you can get a much stronger overall prediction.
Kind of like the wisdom of the crowd.
Exactly. And in this case, they used 10 component models within their boosting framework. And each of those models had specific hyperparameters.
Oh, we love hyperparameters on TalkTensors.
Of course. And the exact details of those hyperparameters, the specific settings they used, that's all laid out in Table 2 of the paper.
Awesome. So we'll make sure to link that table in the show notes for any listeners who want to really get into the weeds.
Definitely.
Okay, so these boosting neural networks, they take these highly informative features and they churn away and produce what they call slice-level confidence vectors. What does that mean?
So remember, we're dealing with CT scans, which are essentially stacks of 2D images.
Right, like slices through the brain.
Exactly. So for each slice, the boosting network produces a vector of probabilities.
Okay.
And each probability represents how confident the model is that that particular slice belongs to each of the 5 ICH subtypes.
So if there are 5 subtypes, there would be 5 probabilities for each slice.
Exactly. So you might have, say, a 90% probability that slice number 10 belongs to the intraparenchymal hemorrhage subtype, a 5% probability that it's intraventricular, and so on.
Okay, so now we have all these slice-level predictions, but ultimately we need a diagnosis for the entire scan, right?
Yeah.
Not just for each individual slice.
Precisely. And that's where their really innovative approach comes in. They use something called an entropy-aware fuzzy integral to combine these slice-level predictions into a scan-level diagnosis.
That sounds very technical. Can you break that down for us?
Sure. So let's start with the entropy-aware part. Entropy, in information theory, is a measure of uncertainty.
Okay.
So if the model is very certain about its prediction for a particular slice, the entropy will be low.
So high confidence, low entropy.
Exactly. And if the model is very uncertain, the entropy will be high.
Okay.
So in their approach, they use the entropy of each slice's prediction to weight that slice's contribution to the overall diagnosis.
Makes sense. The more confident the model is about a particular slice, the more weight that slice should carry.
Precisely. And then we have the fuzzy integral part. Now, fuzzy logic is a way of dealing with situations where things aren't black and white.
Right, like in the real world where things are often fuzzy.
Exactly. And a fuzzy integral is a way of combining information from multiple sources, in this case, the different slices, in a way that accounts for this fuzziness.
Okay, so it's not just a simple average. It's a more nuanced way of combining the information.
Exactly. And the specific type of fuzzy integral they use is called the Choquet integral.
The Choquet integral.
Yeah. And I won't get into the mathematical details here, but essentially it allows them to define a fuzzy measure that reflects the overall importance of different combinations of slices for making the final diagnosis.
So it's not just about how confident the model is on each individual slice, but also about how those confidence levels interact across the entire scan.
Exactly. And they have a parameter in this fuzzy measure called lambda that they tune to capture these interactions.
Lambda, another hyperparameter.
Right. And they actually optimized lambda within a specific negative range because the sum of their entropy-based weights for individual slices was already greater than 1.
Okay. So they're really fine-tuning this process to get the most accurate and informative fusion of information from all the slices.
Exactly. And the end result of this whole process is what they call a fuzzy fusion vector for the entire CT scan.
Okay.
And then, just like with the slice-level predictions, this vector contains a probability score for each of the 5 ICH subtypes. And the subtype with the highest probability is the final diagnosis.
So they've gone from individual slice predictions to a weighted combination of those predictions based on entropy to a final fuzzy fusion vector that gives them the overall diagnosis.
Precisely. It's a really clever and sophisticated approach.
And it seems to work really well. They show some impressive results in the paper.
They do. So first, they compared their PVT model at the slice level against other state-of-the-art deep learning architectures that are commonly used in image analysis.
Okay.
Things like VGG, ResNet, DenseNet.
All right. The usual suspects.
Yeah, and they found that their PVT model performed competitively, so it was already a strong model at the slice level.
Solid foundation.
Exactly. But then, when they moved to the scan level, using their entropy-aware fuzzy integral, they saw significant improvements in performance.
That's where the magic really happens.
Right. They measured performance using a whole range of standard metrics: accuracy, precision, sensitivity, F1 score. And across all of those metrics, they saw a significant boost when they went from the slice level to the scan level.
So their fuzzy fusion method was clearly adding a lot of value.
Absolutely. And they didn't just compare it to doing nothing. They also compared their fuzzy integral approach to other simpler methods for combining the slice predictions, like just taking the mean or using a majority vote.
Right. Kind of like a baseline comparison.
Exactly. And again, their fuzzy integral approach consistently outperformed those simpler methods.
Okay, so it's not just that any kind of fusion is better. It's that their specific method, this entropy-aware fuzzy integral, is really doing something special.
Precisely. And they even tried applying their fuzzy fusion method to other deep learning architectures just to see if it was specific to the PVT.
Okay, interesting.
And they found that even when they used their fuzzy fusion with other architectures, the PVT-based approach still came out on top.
So it seems like the PDT architecture, combined with their fuzzy fusion method, is a really winning combination for this task.
Absolutely. And the paper also includes a really useful comparison against other recently published studies that have tackled ICH classification.
Okay. So how did they stack up against the competition?
Well, they show that their model achieves a very competitive level of accuracy and reliability, which is further supported by the fact that they report the standard deviation of their results across multiple independent training runs.
Right. That's always a good sign. If the results are consistent across multiple runs, it means the model is more likely to generalize well to new data.
Exactly.
Now, all this is really impressive, But it's important to remember that this is just one study. It's not like this AI is ready to be deployed in hospitals tomorrow.
Right. It's still early days. But I think this research is a really promising step forward. It shows what's possible with these advanced deep learning techniques and these intelligent fusion methods.
And it builds on a long history of AI in medical imaging.
It does. I mean, we've come a long way from the early days of rule-based systems and traditional computer-aided detection tools, which often relied on handcrafted features and expert knowledge.
Right, back when AI was more about encoding what we already knew into a computer program.
Exactly. And then came the deep learning revolution, which really changed the game.
Yeah, suddenly we had these models that could learn from the data itself without us having to explicitly tell them what to look for.
Precisely. And CNNs were really the driving force behind that initial wave of deep learning in medical imaging.
Right. But as we've seen, CNNs have their limitations. They're not always so good at capturing these global dependencies, these complex relationships between different parts of an image.
Exactly. And that's where transformers, like the PVT in this study, are really starting to shine.
And then you have these fuzzy logic techniques, which offer a whole new way of dealing with uncertainty and combining information in a more nuanced way.
Right. And explainable AI, which is becoming increasingly important as we want to understand not just what the AI is predicting, but also why it's making those predictions.
So it's all about building trust and transparency, which is essential in a field like medicine.
Absolutely.
So to recap the key takeaways from this paper, the PVT architecture with its hierarchical attention mechanism is really well suited for analyzing these complex 3D CT scans. The SHAP-based feature selection not only improves computational efficiency, but also enhances the interpretability of the model. And the entropy-aware fuzzy integral operator provides a really robust and intelligent way to integrate information from multiple CT slices, accounting for the variability within a scan and the model's confidence levels. And all of this is backed up by rigorous evaluation, including a patient-level data split and multiple independent training runs, which gives us more confidence in the generalizability of their findings.
Right. It's a well-rounded study for sure.
And the potential real-world implications are huge. We're talking about potentially faster and more accurate diagnoses of ICH, which could lead to more timely and appropriate treatments and ultimately better outcomes for patients.
Absolutely. And it could also help to reduce the workload on radiologists, especially in those high-pressure emergency settings.
Right. It's not about replacing radiologists. It's about giving them a powerful tool to assist them in making the best possible decisions.
Precisely.
Now, this brings us to our favorite part of the show, our Novel Notions segment. Based on this research, what are some potential future directions that you'd like to see explored?
So one thing that really struck me is that the study focuses on analyzing static CT scans. You know, they take a snapshot in time.
Right.
But in reality, ICH is a dynamic process. It evolves over time.
Right. The bleeding can get worse. It can stay the same. It can even improve.
Exactly. So research idea number one. What if we could develop a 4D model that incorporates the temporal dimension?
4D, meaning 3D space plus time.
Exactly. So imagine a model that could analyze a sequence of CT scans taken over time and track how the hemorrhage is changing.
That would be amazing.
Right. And then we could potentially use that information to predict the likely course of the hemorrhage.
So will it get worse? Will it stay the same? Will it get better?
Exactly. And that kind of information would be incredibly valuable for guiding treatment decisions.
Absolutely. If you know the hemorrhage is likely to expand, you might take a more aggressive approach. But if it's likely to remain stable, you might be able to take a more conservative approach.
Exactly. So I think building these 4D models, these models that can incorporate temporal information, is a really exciting research direction.
I completely agree. And it ties in nicely with the growing trend of longitudinal medical imaging data.
It does. We're collecting more and more data over time, so we need models that can actually make use of that temporal information.
Right. It's not just about analyzing individual snapshots anymore. It's about understanding the whole story, the whole trajectory of the disease. Okay, what's research idea number 2?
So research idea number 2, data augmentation.
Data augmentation.
Yeah. So the data set they used in this study was pretty substantial, but certain rare subtypes of ICH might still be underrepresented.
Okay, so even with almost 850 patients and nearly 2,000 CT scans, there might still be some edge cases that the model hasn't seen enough of.
Exactly. And that could potentially limit the model's ability to generalize to those rarer cases.
Right, because the model might not have learned the subtle features that distinguish those rare subtypes.
Precisely. So one way to address this is to use data augmentation techniques.
What does that mean?
So data augmentation is basically a way of artificially increasing the size of your data set.
Okay.
And you do this by creating synthetic data points that are similar to your real data points.
So it's like creating fake CT scans.
In a way, yes, but these fake CT scans have to be realistic. They have to capture the same kind of patterns and variations that you see in the real data. And there are a lot of different techniques for doing data augmentation. You can rotate the images, you can flip them, you can add noise. You can even use generative adversarial networks or VAEs to create entirely new images from scratch.
So you're basically trying to trick the model into thinking it has more data than it actually does.
Exactly. And the hope is that by training on this augmented data set, the model will be more robust and will generalize better to those rarer cases.
So it's like giving the model a wider range of experiences to learn from.
Exactly.
And in the case of ICH, you could imagine using data augmentation to create synthetic CT scans that depict those rarer subtypes, or maybe scans that show the hemorrhage at different stages of progression.
Precisely. And I think that could really help to push the boundaries of what's possible with these AI models.
Absolutely. Both really insightful research ideas. Thanks for sharing those. Well, that concludes our deep dive into this fascinating paper on automated intracranial hemorrhage classification. It's a great example of how AI is being used to tackle some of the most challenging problems in medicine. And it highlights the importance of not just developing new deep learning architectures, but also thinking carefully about how to select the most informative features, how to combine information from multiple sources, and how to build models that are both accurate and interpretable. We'll be sure to link to the paper in the show notes so you can check it out for yourselves. And we'll leave you with this thought. If we can achieve such promising results in the challenging domain of ICH, what other areas of medical imaging could benefit from these kinds of advanced AI techniques? The possibilities are truly exciting.
Yeah.
Thanks for joining us on TalkTensors. Until next time.